show, but this is not marked, the midterm is not marked yet. It was hard. Well, yes, we know it was hard. It was supposed to be harder than the usual quizzes, because all quizzes are kind of easy marks. You just prepare well and you get the marks. The midterm and the final should be kind of harder exams, and so you should also show that you can think about stuff which you haven't seen exactly the same stuff. Well, we'll see how it goes. Maybe if the marks are too low, we'll adjust them a little bit.
Then there will be even fewer people. You just later go.
We'll see how it goes. Well, so I can't tell you anything because the quiz is not marked yet. From what I've seen, half of the people didn't solve the first problem. The first problem was about like something like directly from what we covered. Like, here's an equation, quadratic equation, find parameterization for solutions. So if you don't solve this, it means that you just didn't prepare.
We were still using the equation.
Just quadratic equations. It doesn't matter. The geometry just doesn't matter. Well, so I posted the solutions to the midterm online. You can find the solutions. So on this solution, there are many ways to solve each one of the problems. I posted for kind of the shortest solutions of M2. For each question, there are many ways. For example, there was a question with something like finding 3 to the power 1000. Of course, you can do it by successive squaring. That's not the way. So,
do we get any mark if you did it correctly?
yeah, you get full marks if you did it correctly. But, you know, I'm not sure that somebody could do it correctly with successive squaring. But anyway, so today I want to start talking about the questions like this. Suppose you are given some number modulo prime, and you want to understand is it a square or is it not a square. So say in real numbers, it's very easy to understand whether a number is a square. If you see a minus sign in front of it, it's not a square. If it's plus something, it is a square. But if you look at numbers modulo prime, it becomes a, well, not real question. Is it, can you find some number whose square is 3 modulo 7? Well, a priori it seems like you have to actually try it. 1 square, 2 square, 3 square, all the way up to 7 square. So what I'm going to talk about is that there are more efficient ways to understand whether a given number is a square modulo prime b. And well, today we'll just start. We'll start with easy parts, and next lecture we'll cover what's known as quadratic reciprocity. It's some very beautiful theorem, very efficient way to answer this question, and well, maybe it will be our second kind of large theory. The first one was existence of primitive root modulo p. Quadratic reciprocity will be the second kind of big part of the theory. But today we'll start just preparing ourselves. And another thing that I want, well, I hope that it will come to today is this question. Is there some polynomial with integer coefficients which doesn't have integer roots, but such that the congruence f of x is equal to 0, modular prime number p is solvable for every prime p? So once again, I mean, you're given some congruence, something like x cubed plus x minus 1 is congruent to 0 modulo. And you want to understand, is it true that it has a solution modulo every prime p? There is an obvious kind of reason why it could have a solution. For example, this congruence definitely has a solution for every prime p, just because x equal to 1 is an answer. So x equal to 1 modulo p is always an answer, but just because x equal to 1 is a solution of this this problem. X cubed plus x minus 2 is equal to 0, just literally equal to 0. X equal to 1. So if you have a solution with integers, definitely you can reduce it modulo a prime and get a solution modulo a prime. The question is there some polynomial in which there is a solution modulo a prime, but no integer solutions? So we hope that we will consider this problem, answer this problem today. So now back to so that's kind of brain teaser, but if you get bored by what I'm doing, try to think about this. Okay, so now, once again, the question is which will understand something about this one. I want to understand, given A, is it a square or is it not a square? Basically something like this. Given, oh, I'm asking something like, is 3 a square modulo 7? Is there some number whose square is congruent to 3 modulo 7? Something like this. So, first thing is an observation. So let me first give a definition of quadratic residue. We say A is a quadratic residue. First of all, I want to take it on 0. Somehow the theory works much better if you always assume the quadratic residues are non-zero. Just part of my definition. And A is congruent to x squared modulo b. So if something is a square or something else, we say it's a quadratic residue. The quadratic non-residue is just something which isn't. So A is a quadratic non-residue. If A is congruent to x squared modulo b, has no solutions. So the task is somehow to describe what are the quadratic residues modulo prime b. First observation is like this. Usually about half of the numbers of quadratic residues, half of the numbers of quadratic non-residues. So first our third theorem. If p is odd, then of the numbers 1, 2, up to minus 1, exactly half are quadratic residues, half are quadratic non-residues. So let me demonstrate it. Example, b is equal to 7, quadratic residues, quadratic non-residues. Oh, 1, let's start with 1. Is it quadratic residue or quadratic non-residue?
Itself, but it's just a square.
Yes, 1 is just square of 1 of 1. So 1 is definitely a residue. So maybe let's do it like this. Let's find all the residues. It seems very easy to actually find all the residues, all the quadratic residues. Just take all numbers, square them, and you'll get all quadratic residues. So 1 squared is 1. 2 squared is 4. 3 squared is 2. Right. Sorry? Instead of why? because it's so these are the answers. I mean, it's 1 squared, 2 squared, 3 squared, now 4 squared. Actually, I don't have to compute 4 squared because it's the same as minus 3 squared modulo 7. So actually, minus 3 squared, minus 2 squared, and minus 1 squared are already here. And well, 0 squared doesn't count just because of my strange definition. Just all 0 is always, well, it is not relevant. And all the rest are just non-residues. So it's 3, what else is missing? 3, 4, 1, 2, 3, 4, 5, 6. So you see that in this case, 3 of the residues are quadratic residues, and 3 of them are quadratic non-residues. And in general, how can I prove such a fact? Well, the quadratic residues are just something squared. But if you consider this procedure of how to find the quadratic residues, well, we take all the numbers from 1 to p minus 1, square each one of them, and get the quadratic residues. But when we are doing this procedure, we are every time gluing two numbers to the same output. If you take 1 squared or minus 1 squared, you always get the same answer. If you take, so the mapping x goes to x squared is from the numbers from 1 to p minus 1 to, I'm sorry, this set to itself. Oh, it always glues, it's 2 to 1. It takes every, well, it glues exactly two different numbers to the same output. Plus or minus x squared is the reason is x squared is equal to 8 always has either 0 or 2 solutions. And the solutions differ by just multiplying them by minus sign. So we just take, well, all the numbers from 1 to p minus 1. We have this method and it pulls two different numbers to the same output, and I mean plus minus x goes to the same number x squared. So the image covers half of, well, the number of the images is half of the numbers of the inputs. Number of outputs is half of the number of the inputs. So you get exactly p minus 1 divided by 2 quadratic residues, and all the rest are quadratic non-residues. Okay, that's some information. You know that half of the numbers are residues, half of the numbers are non-residues, but which half and how they are located. For now, not always. Okay, next thing. We already know something, well, something very, very strong. We know that modular prime number p, there always is a primitive root. So maybe we can describe these residues, or quadratic residues, quadratic non-residues, in terms of this primitive root. Of course, the task of actually finding the primitive root is very hard. But let's try to understand what are the quadratic residues if we know the primitive root. So if alpha is a primitive root, modulo p, the quadratic residues are what are they? If you take just p, yes. Okay, well, every number is out of the sum power. But what is special about the powers of alpha, which are quadratic residues?
Even power?
Even powers, yes. Well, alpha to the power of 2k. The reason is, well, such a number for some k. And that's all this. Just because take any number x, it is some power of the primitive root, alpha to the power k. Then x squared is alpha to the power 2k. So every square is an even power of the primitive root. And of course there are half of the powers are even, half of the powers are odd. So there are half of the residues are quadratic residues, half of them are not quadratic residues. So maybe I can write the explanation. So if a is x squared modulo b and x is alpha to the power k, then a is alpha to the power 2k. Okay, so if you know some primitive root, all the even powers of this primitive root will be quadratic residue. In this example, I think that 3 is a primitive root, and then we can take 3 squared to the 2, 3 to the 4th is 2 times 2 is 4, and 3 to the 6th is 1. So we can just check it here. Okay, so that's good. But once again, this there is some problem with this description, and the problem is it's usually hard to find a primitive root modulo prime. But now there is a funny property. If you take 2 squares and you multiply them, you always get another square. So maybe another theorem. If you take a quadratic residue and multiply it by another quadratic residue, you get a quadratic residue. That's all this. And x squared times y squared is xy squared. If you take a quadratic residue and multiply it by quadratic non-residue, what are you going to get? Well, not a quadratic residue. I have two ways of explaining this. One is kind of elementary. Suppose that to the contrary that you take something of the form f squared, multiply it by something and get something of the form y squared. So if x squared times something is z squared, even modulo p, then this something must have been a quadratic residue. Indeed, it should have been z times the inverse of x squared. I mean, we know we can do arithmetic operations modulo prime, we can divide by any non-zero number modulo prime. So that's all this. If you take the quadratic residue and multiply it by something, if you get a quadratic residue, then this something was a quadratic residue. Here's a formula. Another explanation, well, quadratic residue is a primitive root in even power. This is a primitive root in odd power. So the product is primitive root to the power of odd plus even. So it is odd. So it's not residue. And finally, a theorem which is, well, the heart of the theory. If you take the quadratic non-residue, and multiply it by another quadratic non-residue, you will get quadratic residue. Now, this last part, well, it's really not that elementary. I mean, you take something which is not a square, you multiply it by something which is not a square. Why should you get something reasonable? Well, not only it's something reasonable, it is always a square. It doesn't tell you which square it is, but, well, it is some square. The reason is, well, once again, alpha to some odd power, times alpha to some odd power is alpha to some even power, which is the quadratic residue. Okay, so it tells us that if you take, if you look at the set of all quadratic residues and quadratic non-residues modular prime number, so if you recall, say, example, modular 7, quadratic residues are 1, 2, 4, quadratic non-residues are 3, 5, 6. So if you multiply any two numbers in the first row, you get a number in the first row. If you multiply any number here by any number here, you get a number here. And what's most funny is if you take the product of any two numbers in the second row, you're going to get a number from the first row. So there is some structure to this quadratic residues, and fine multiplicative structure. They behave well relative to multiplication. But still, I mean, yes, on the set of all quadratic residues, there is some kind of fine structure. But still, I give you a number, how to determine whether it is a quadratic residue. So let me give you an answer, or one answer. The quadratic residues, once again, theorem, quadratic residues modulo P are exactly the solutions of the following equation. X to the power P minus 1 divided by 2 is congruent to 1 modulo P. So this theorem gives you a natural procedure how to determine whether something is a quadratic residue. Saying that it's a quadratic residue turns out to be equivalent to saying that it's the solution of this equation. It means just take this number, raise it to the power P minus 1 divided by 2. If you get 1, it is a quadratic residue. Kind of fine theorem, but it's also not very hard theorem. Well, given what we already know. First thing, if something is a quadratic residue, it's obviously a solution of this thing. If x is y squared modulo p, then x to the power p minus 1 divided by 2 is y to the power p minus 1, which is congruent to 1 modulo p. Fermat theorem. So all quadratic residues are solutions. And how many solutions do you find this way? How many quadratic residues are there?
P minus 1.
Yes, P minus 1 divided by 2. So quadratic residues are P minus 1 divided by 2 solutions of this equation. But how many solutions could it have? Well, at most P minus 1 divided by 2 solutions, because it's a polynomial congruence modulo prime number. We know that the number of roots of polynomial modulo prime number is at most equal to its degree. So since this congruence comes to more solutions, more than P minus 1 over 2 solutions, quadratic residues are exactly its solutions. So once again, the logic is like this. we know that all the quadratic residues are solutions for more or less obvious reason, and there are a lot of them, p minus 1 divided by 2. But such an equation cannot have any other solutions. It cannot have more than p minus 1 divided by 2 solutions. So the quadratic residues are exactly the solutions.
Yeah, so now no solutions for polynomial modular prime
Modular
is
prime.
maximum. But if it's modular non-prime,
Modular non-prime, it's not. For example, we've seen something like this. Maybe x squared is equal to 1 modulo, say, product of two numbers, 3 times 5.
for example.
Could have four solutions. Yes. So it is important to piece prime. Okay, so this gives us kind of criteria. It actually got a name. It's called order criterion. So order criterion. A is the quadratic residue, if and only if a to the power of p minus 1 divided by 2 is congruent to 1 modulo b. So example, say I want to understand is 3 the quadratic residue modulo 7. Well, my first attempt would be just try all possible squares and this one will connect to 3. But here's a less direct procedure. I take 3, raise it to the power 7 minus 1 divided by 2. It's 3 cubed. Now I compute this by successive pairing together. So it's 2 times 3, it's minus 1 modulo 7. So the conclusion is not equal to 1. So 3 is quadratic non-residue. Let's introduce a notation. The notation is like this. It's called Legendre symbol. Looks like this. A divided by p and brackets. It's just Legendre symbol a modulo p, and b is like this. It's a to the power of p minus 1 divided by 2 modulo p. So this very number, a to the power of p minus 1 divided by 2, is just give it a name. I want to say something about this number. So we know that it's equal to 1 if and only if a is a quadratic residue. If a is not a quadratic residue, well, for now we know it's just not equal to 1, but I can say more. So a over p is congruent to 1, is equal to 1 if and only if a is quadratic residue, and I claim that this number is equal to minus 1 if and only if a is quadratic non-residue. So it's not a coincidence that we got here minus 1, we always get either plus 1 or minus 1. And let me give a proof. If I take this number, say x is a to the power of p minus 1 divided by 2 modulo p. So if x is not equal to 1, if x, so first thing, x squared, if I take x squared, is definitely equal to 1. It is a to the power of p minus 1, and we know it is equal to 1 just by permeable sphere. So the square of x, the square of this number is always equal to 1. It means that it's always either 1 or minus 1. So hence x is plus 1 or minus 1 always. And we already proved this theory. It is equal to 1 if and only a is a quadratic residue. So if it's not a quadratic residue, it must be that possibility, minus 1. So this notation, in other words, it just distinguishes the two cases. When a is a quadratic residue, it gives you 1. If a is a quadratic non-residue, it's minus 1. With this notation, what we proved about this thing about multiplying quadratic residue with quadratic non-residue, given the quadratic non-residue, and so on, looks like this. If you take the product of two numbers and you want to determine whether it is a quadratic residue, so you want to compute the Legendre symbol of AB modulo P. It is the same as such a product. Indeed, how can you get plus 1 here? Well, if A times B is a quadratic residue, if and only if either both A and B are quadratic residues, or if both A and B are quadratic non-residues. Another proof, well, here is a simpler proof. Proof A times B to the power of B minus 1 divided by 2 is the same as, or actually the same as A to the power of B minus 1 divided by 2, B to B minus 1 divided by 2. So that's a different proof of the same identity. So the Legendre symbol is kind of multiplicative. Let me give you an answer to the, maybe the first material question. When is minus 1 a quadratic residue? Yeah?
X to the permitted root.
When what?
X to the permitted root or 8.
What's 8?
Like, if you take a permitted root raised to the power p minus 1 over 2, then you eliminate 1.
Yes. Oh, I see. Actually, if you take a primitive root and raise to the power of p minus 1 divided by 2, you always get minus 1. Oh, I see. I see what you mean. You say that, well, take, I see, alpha a primitive root, modulo p. I see, yes. It's a good way to explain this. Minus 1 is alpha to p minus 1 divided by 2 modulo p. Because you know alpha to the power of p minus 1 is equal to 1, so this number squared must be equal to 1, but it itself cannot be equal to 1. The smallest power you should raise alpha to get 1 is p minus 1, not p minus 1 divided by 2. So this number is minus 1. And we know that only even powers of alpha give you quadratic residues. So minus 1 is a quadratic residue, if and only if p minus 1 divided by 2 is even. Next. So, on the property right, it is saying that p is equal to 1 modulo 4. So we know, for example, that modulo 13 minus 1 is a square of something. We have no idea of what. I mean, it's not hard to find what, but it gives you information without actually trying all the possibilities. So maybe I wanted to give, so answer 1. Another answer, maybe kind of a little bit more straightforward. If I want to compute whether minus 1 is a root or not, Well, I know what to do. I should take -1 and raise it to the power of p minus 1 divided by 2. What do I get? Well, this is 1 if the number b, p minus 1 divided by 2 is even. So, another explanation for the same result using slightly different approach. So let me give you an example how this could be useful. Example. Let's say I want to understand whether phi, whether 3, yes, this one too. Whether 3 is a quadratic residue modulo 7. Well, how can I do it? Here's the thing. Let me write 3 as -4. 3 and -4 are the same number, modulo 7. Now, the Legendre symbol is multiplicative. I can write -4 as -1 times 4. So it is -1 and 4. Now, I know what is this thing. It is, well, it is equal to -1 because 7 is not 1 modulo 4. That's our result. So it is -1 times, what about 4 modulo? 4, well, the Legendre symbol of 4 modulo 7. 1. 1, because obviously 4 is 2 squared. It's just, it is a square. So it is -1. So once again, in such a kind of funny way, we get the result of this quadratic non-residue modulo 7. Okay, so once again, for now, let's say for today, we just learned the following facts about quadratic residues. One thing, modular prime number, there are half of the things, half of the residues are quadratic, half of the residues are non-quadratic. Another thing, you can encode quadratic, whether something is quadratic residue or quadratic non-residue by this kind of funny symbol, and there is a funny multiplication rule. The product of these symbols is equal to the symbol of the product. So that's one of the facts that we know. Another fact is to determine whether A is a quadratic residue, there is a kind of efficient procedure. You can take A to the power p minus 1 divided by 2 modulo p and decide whether it's +1 or -1. And we know that to compute this, it's pretty fast. You can do it by successive squaring, for example. And what else? And maybe we have the answer of what is -1 or whether -1 is a quadratic residue. The answer is it is equal to 1 if and only if is 1 modulo 4. More or less, that's what we know about quadratic residues for now. And for today, we'll stop here about the quadratic residues. And next time we'll see much more, well, much deeper result about quadratic residues. It turns out that modulo different primes, we'll see what will come. We'll have very fast and efficient procedure for how to compute this Legendre symbol, how to decide whether something is a quadratic residue. We'll see, we'll talk about the future in the future. But for now, let me come back to this question. So the question is there some polynomial with integer coefficients such that for every prime such that for every prime the equation f of x is equal to 0 has a solution, but in general it has no solutions in integers. No integers. Okay, so maybe something like this. But this is not good enough because, well, yes, it doesn't have any integer solutions, but it doesn't have a solution always, modular prime. This thing has a solution if and only if p is congruent to 1 modulo p in modulo 4, so not always. You can try other things. You can try, well, maybe x squared minus 4 is congruent to 0 modulo p. It has a solution for all p. But it's not good enough also, because x equal to 2 is a solution of the usual equation, x squared minus 4 is equal to 0. Did anyone have any idea about how to construct such a polynomial? So the answer is, yes, there is such a polynomial which has a solution modulo every prime, but doesn't have any integer solutions. Did anyone have an idea? Okay, let me give you an answer, and then we'll try to figure out why it is the correct answer, or why it is the correct answer. So let me try such a polynomial. X squared minus 2 times x squared minus 3 times x squared minus 6. Well, one obvious thing, this polynomial has no integer solutions. Well, indeed. If this thing is equal to 0, then x is plus minus square root of 2, or plus minus square root of 3, plus minus square root of 6. Definitely, none of these things is an integer. So let me write this down while you're thinking why this thing does have a solution modulo every prime. F of x is equal to 0. There's no integer conditional solutions. Its roots are plus minus square root of 2, plus minus square root of 3, plus minus square root of 6. Now, let's look at the congruence f of x is congruent to 0 modulo p. Well, still it has the same kind of roots. Square root of 2, square root of 3, square root of 6. So if one of these square roots actually can be extracted modulo p, if either 2 is a square of something, or 3 is a square of something, or 6 is a square of something, then we will find a solution. But is 2 a square modulo prime p? Well, you know, sometimes yes, sometimes no. It's not obvious. Is 3 a square modulo prime p? Same answer. Sometimes yes, sometimes no. Same about 6. But there is something funny. Suppose that 2 and 3 are not quadratic residues modulo prime p. That you cannot extract the square root of 2 and you cannot extract the square root of 3. Then the claim is that you can extract the square root of 6, because 6 is a product of 2 and 3. And if you take a product of 2 quadratic non-residues, you always are going to get a quadratic residue. And for this, well, if you recall, we actually had to use primitive element theory, so it's not that obvious. So yes, there is always a solution modulo p. What solution? Hard to know. So f of x is congruent to 0 modulo p has a solution. 2 is 2 is congruent to x squared modulo b, or 3 is congruent to x squared modulo b as a solution. Then we are done. Just take this x, which is a solution equal to this or this, plug it into here, and you get the 0 f modulo prime p. If none of them has solutions, so if however neither 2 nor 3 are quadratic residues modulo prime p, then the product is a quadratic residue. 3 times 2 is quadratic residue modulo p. So x squared is congruent to 6 modulo p has a solution.
So you chose 2 and 3 specifically because they were numbers. It's not a case of you just start checking.
No, of course not. I want to solve such congruence. X squared minus 2 times x squared minus 3 times x squared minus 6 is congruent to 0 modulo p. What does it mean that the product of three numbers is divisible by prime p? It means that one of them is divisible by p. So this is equivalent to saying that x squared is congruent to 2 modulo p, or x squared is congruent to 3 modulo p, or x squared is congruent to 6 modulo p. So existence of solution of this equation is the same as existence of solution of one of these three equations.
So, I need to first.
Yes, of course there is nothing magical about 2, 3, and 6, except that 2 times 3 is equal to 6. So you could have chosen 5, 7, and 35. So you just should be careful. You should not choose, say, 4, 3, and 12. Because 4 will spoil it. X squared minus 4 has an integer solution. No, prime is not squares. Not integer squares. 2, 3, and 5, no, we won't. Next time we'll see how to determine all the primes to be both 2, both 3, and 5 quadratic bases, and we'll see that it's not all the primes. So there are primes to which neither 2, 3, nor 5 quadratic bases. One square minus 1. So you don't have yes, plus 1 x squared minus 3 and x squared plus 4.